A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, Assalamu alaikum wa rahmatullahi wa barakatuhu. Today it's our 21st lecture on powder X-ray diffraction, and the course is X-ray diffraction techniques. Course code CAM 5134. Dear student, the key concept of our today lecture are spectroscopy, and in spectroscopy we discuss different terminology, then different methods of spectroscopy, photon interaction, journal history of synchrotron X-rays, synchrotron science, radiation from bending magnets. Synchrotron radiation is electromagnetic radiation. What is a synchrotron? Development of the synchrotron. And in the last of today's lecture, we discuss how does a synchrotron work. Now we start from spectroscopy. In fact, spectroscopy is the interaction of electromagnetic radiation with matter, as you know. Valence electron show chemical bonding, while core electron do not take part in any interaction, and ionization result in photoelectron spectroscopy. Here you can see in this diagram, when electromagnetic radiation fall on the matter, result in diffractogram. In case of spectroscopy, core electron and valence electron result in electron spectrum. Now we discuss different methods of spectroscopy like X-ray diffraction, photoelectron spectroscopy, included core level electron spectroscopy, valence band photoemission, resonant photoemission, photoelectron diffraction, and next is X-ray absorption spectroscopy, which include near edge X-ray absorption spectroscopy, extended X-ray absorption fine structure, X-ray magnetic circular dichroism, X-ray emission spectroscopy, including resonant inelastic X-ray scattering. Now, what is photon interaction? Incident photon interact with electron, core and valence, मीन जो कि इलेक्ट्रॉन आपके वैलेंस और कोर के अंदर हैं. Here is the incident photon radiations, fall on object, and interact with both valence and core electron. Photon is absorbed, elastic scattered or inelastic scattered. Electron is emitted, excited and de-excited. So जब फोटॉन आपका इंटरेक्ट करेगा तो इलेक्ट्रॉन आपके या emitted होंगे या एक्साइटेड होंगे या de-excited. And now detected particle मीन जो इंटरेक्शन के रिजल्ट में आपके पास पार्टिकल आएंगे उनके रिजल्ट में आपके पास कौन सी स्पेक्ट्रोस्कोपी होगी. emitted particle इलास्टिक स्कैटरिंग मीन जब इलास्टिक स्कैटरिंग होगी एक्स-रे डिफ्रैक्शन phenomena or spectroscopy in the form of speckle. Speckle actually जो आपके पास like single crystal एक्सरे जो है उसको जब आप करते हैं तो फिल्म के ऊपर ब्लैक स्पॉट आपके जो अपीयर होते हैं, वाइट और ब्लैक स्पॉट जो हैं उनको हम क्या कहते हैं, जो अपीयर होते हैं वो फिनोमिना जो है वो स्पेकल कहलाता है. Then inelastic scattering result in X-ray emission spectroscopy. Electron emission result in photoelectron spectroscopy. And when no emitted particle mean photon absorbed result in X-ray absorption spectroscopy. Now Journal History of Synchrotron X-rays. X-rays were discovered in 1895 and synchrotron X-rays were first observed in 1947. Initially, synchrotron X-rays were considered an undesirable effect, but in the 1960s, they began to be recognized as an exceptional tool. In 1895, Roger discovered mysterious rays capable of passing through the human body. Because of their unknown nature, he called them X-rays. In 1912, Liu and Knipping obtained the first diffraction pattern of a crystal using X-rays. In 1953, the structure of DNA was solved by Watson, a biologist, and Crick, a physicist, thanks to the use of X-rays. Although these results were remarkable, the X-ray tube were limited. The light was emitted in all directions with no possibility of focusing it or making the rays parallel. This light was also only intense at particular wavelength, which restricted its use, particularly in the field of spectroscopy. It is William Roger who discovered X-rays, and he got Nobel Prize in Physics 1901. And here is the print of the left hand of Anna Bertha Lewis Roger, 22nd December 1895. This is the first X-ray. Synchrotron science. Synchrotrons provide flexible, powerful method for learning about the structure and behavior of matter at the molecular and atomic level. A synchrotron is a stadium-sized machine that produces many beams of bright X-ray light. Each beam is guided through a set of lenses and instruments called a beamline, where the X-rays illuminated and interact with the samples of material being studied. Many countries operate synchrotrons. There are 10 in Europe alone, but only 4 worldwide are similar to the European Synchrotron Radiation Facility in terms of design and power. This picture shows various parts of synchrotron, but here is only I am going to show you the bending magnet. If we magnify only this part, we can say here is the bending magnet, and these are the other different parts of synchrotron. We will discuss these parts in next slide in detail. Synchrotron radiation is electromagnetic radiation. This is the whole diagram or picture relating to the radiation and their wavelength and energy with different objects. In this diagram, we see here is the spectral range covered by synchrotron radiation here, and this diagram also shows the relation between wavelength and energy with different objects. Synchrotron radiation is electromagnetic radiation emitted when charged particles are readily accelerated, mean moved on a circular path. Here is the charged particle, mean electrons circulating in a storage ring and produce synchrotron radiation, which passes from beam collimator, and here is the magnetic field. What is synchrotron? A synchrotron is a particle acceleration device which, through the use of bending magnets, causes a charged particle beam to travel in a circular pattern. स्टूडेंट, ये आपके पास ओवरऑल सिंक्रोट्रॉन का सेटअप है। यहाँ पे डिफरेंट मैग्नेट आपके यहाँ पे यूज किए जाते हैं और इसी के अंदर यहाँ पे आपके पास जो है वो एक्सेस जो है वो प्रोड्यूस होंगी। ये जो है यहाँ पे, ये जो यहाँ पे बेंडिंग मैग्नेट हैं और यहाँ पे डिफ्रैक्शन, और इनको डिफरेंट जगह पे आप रेज को फिर यूज कर सकते हैं। ये देखें यहाँ पे कि ये आपकी बीम लाइन है और ये एक्सपेरिमेंट्स यहाँ पे, यानी कि ये जो बेंड यहाँ पे आ रहा है, यहाँ पे आपके डिफरेंट एक्सपेरिमेंट जो है वो परफॉर्म किए जाते हैं। तो ये एक स्टेडियम साइज आपका जो है ये सेटअप होता है। डिफरेंट इसके पार्ट्स हैं, आगे हम इनको डिटेल से डिस्कस करते हैं। A synchrotron is an extremely powerful source of X-rays. It builds on the physical phenomenon that a moving electron emits energy when it changes direction. If the electron is moving fast enough, The emitted energy, called synchrotron radiation, is at X-ray wavelength. Synchrotron radiation is produced by electrons that circle inside an accelerator ring. When these electrons, which travel at nearly the speed of light, are guided into a curve by deflecting magnets, they emit a highly intense and collimated beam of light whose spectrum ranges from infrared light to X-rays. Even more effective than deflecting magnets are special magnets known as wiggler and undulators. They are used in storage rings and consist of a series of alternating pairs of magnets extending over several meters. This magnet racetrack forces the superfast electrons to speed up along a narrow zigzag channel. Here, a complete setup of synchrotron. These are wiggler, undulators, quadrupoles here, radio frequency cavity, bending magnets. In undulator, you can see insertion device, which is form of magnet, and in bending magnets, you can say here is the bending magnet and synchrotron light passes from these magnets, which used in different experiments. Due to the large number of successive magnets poles, the electrons emit a much more intense beam of light than that produced with the single deflecting magnet. Use of a wiggler generates synchrotron radiation up to 100 times as intense as that produced with deflecting magnets. In a certain mode of operation, the intensity at specific wavelength can even be 1,000 times higher because the wave trains reinforce one another. As a result, the wiggler is transformed into an undulator. Synchrotron radiation is millions of times more brilliant than anything a physician X-ray machine can produce. Scientists use it to study the most diverse materials with atomic precision. These materials range from metals and semiconductors to plastic and protein molecules. Summary about synchrotron. Synchrotron is a cyclotron wherein the strength of magnetic field increases with the energy of particles to maintain their orbital radius constant. It is an incredibly powerful source of X-rays. These are generated by high electrons moving in a large circle of the synchrotron. The whole world of synchrotron science is based on a physical phenomenon, that is, a moving electron changes its direction, emit energy. As the electron moves fast enough, the energy emitted is of X-ray wavelength. And now what is cyclotron? It is an apparatus in which charged atomic and subatomic particles are accelerated by an alternating electric field while following an outward spiral or circular path in a magnetic field. Development of the synchrotron. We can also view the impact of the synchrotron on the development of X-ray generation technology during the 20th century in terms of available spectral brightness. The X-ray tube has steadily increased in power as a result of various technological improvements, particularly with the introduction of the rotating anode X-ray tube in the 1960s. The curve above then arced upward dramatically with the introduction of the synchrotron. You can say here is the electron impact X-ray tubes introduced, and then rotating anode X-ray tubes introduced in this era, and then bending magnets, wigglers and undulators. This is the development of the synchrotron. How does a synchrotron work? A synchrotron machine accelerates electrons at extremely high energy and then makes them change direction periodically. The resulting X-rays are emitted in dozens of thin beams, each directed toward a beamline next to the accelerator. The machine operates with periodic short and long shutdowns day and night. It is a fundamental principle of physics that when charged particles are accelerated, they give off electromagnetic radiation. An everyday example of this effect is the radio transmitter, in which the particles being accelerated are the electrons in the transmitter mast. Here the acceleration are such that the radiation produced is in the radio frequency range. The most common synchrotrons also use electrons through their speed and acceleration is such that they produce electromagnetic radiation that is not only in the radio frequency range but also in the infrared, visible, ultraviolet and X-ray portion of the electromagnetic spectrum. However, we must first discuss the building block of synchrotron, the so-called dipole magnet, which produces a vertical magnetic field H in the gap between its pole. The dipole magnet has two vital roles in the synchrotron. First, we recall another basic principle of physics that if an electron traveling in a direction v, which is horizontal in the above diagram, v intersect a magnetic field H in a direction perpendicular to v, H is vertical in this diagram, then it will experience a force F, which is called Lorentz force, which is in a direction perpendicular to both V and H, inwards as in this diagram. Since the electron is moving with velocity v, F produces a centripetal acceleration, causing the electron to move in a circular orbital or orbit. The second vital feature is that because the electron is being accelerated within the dipole magnet, it will emit electromagnetic radiation. However, we will return to this second essential ingredient later in next slide. By ganging up a series of such dipole magnets around a circle of the appropriate radius, it is obviously possible to make an electron move around a closed loop consisting of curved mean within the dipole magnet and straight mean between the dipole magnet sections. This would comprise a simple synchrotron, often referred to more properly as a ring or storage ring. Though there are several other aspects and components to consider. First, we need a source of energetic electrons to feed into the ring, and this is done using a linear accelerator, mean LINIC, which produces electrons at energies which can range from hundreds of megaelectron volt to several gigaelectron volt. Here is the diagram of synchrotron. यहाँ पे आप देख सकते हैं ये आपके विगलर हैं, ये बेंडिंग मैग्नेट, ये आपके इंजेक्टर मैग्नेट, अनडुलेटर, वैक्यूम चैम्बर, रेडियो फ्रीक्वेंसी कैविटी, डायरेक्शन ऑफ इलेक्ट्रॉन बीम, करंट मीन फ्रॉम दिस टू दिस। यहाँ से आप देखें ना कि यहाँ पे आपके जो हैं बेंडिंग मैग्नेट से आपकी रेडिएशन जो एक्सरे जो है वो पास हो रही है डिफरेंट एक्सपेरिमेंट की तरफ। क्लियर? With some synchrotrons, a small booster synchrotron sited in between the LINIC and the main synchrotron is temporarily used during the startup, which is referred as injection, just to bridge some of the energy gap between the output mega electron volt of the LINIC and the input giga electron volt required of the main synchrotron ring. A key aspect of injection, however, is that the electrons are injected in discrete pulses so that the electron exists inside the storage ring as bunches, typically 1 or 200 bunches distributed around the whole ring. This is essential for an effective action of another synchrotron component, a radio frequency generator or cavity of which there could be several around the ring. The purpose of this device is to synchronously, hence the name synchrotron, feed energy to the electron bunches circulating in the ring to compensate for their energy losses during their emission of radiation. This current of electron bunches slowly decays with the time due to collision between the electron and any molecules contained within the ring. Even with ultra-high vacuum condition, typically 10 to minus 10 millibar in the storage ring, the storage beam typically need to be regenerated about every 24 hours. A very basic plan of for a synchrotron might be as shown in this diagram. The brown lines denote the path of the synchrotron radiation emitted as the bunches of electrons passes through the dipole magnets. This produces a Catherine wheel effect. Here you can see in this diagram, these are the radio frequency generator building, X-ray beam line, main synchrotron storage ring, booster synchrotron, linear accelerator, brown line showing the synchrotron radiation emitted as the bunches of electron passes through the dipole magnet. और यहाँ से ये जो बेंडिंग मैग्नेट हैं, यहाँ से एक्सरेज आपकी जो है वो कलेक्ट की जाती हैं डिफरेंट लेबोरेटरी की तरफ, और ऑफिस बिल्डिंग यहाँ पे डिफरेंट. तो दिस इज द होल पिक्चर ऑफ सिंक्रोट्रॉन. Dear student, here is the end of our today lecture relating to synchrotrons. And in this lecture, if you have any question or difficulty in understanding, you can send me your question at my email ID maslamchemist@hotmail.com. Thank you so much, dear student. Take care. Allah Hafiz.